Hello, good evening. So, welcome to this session of BARTI. So, today we will be discussing quantum mechanics in continuation with the last lecture. So, we have discussed various phenomena related to quantum mechanics. Various basic of quantum mechanics also we have discussed in previous sessions. So, friends, as we know, we have seen how quantum mechanics emerges from the classical mechanics and how quantum mechanics are differ from the classical mechanics. Because the basic difference in between these two mechanics is that we are considering mostly the microparticle in quantum mechanics, whereas macroparticle in classical mechanics. So that is the broader classification. But again, there are so many aspects by which we can classify the quantum mechanics and classical mechanics with each other. Another discussions we have seen how the trajectory would be if we are just throwing or just we can say ejecting the electron from any of the metal surface or any of the means simply as we know from where electron can be emitted. So then again we know if there is a emission of electron, then how trajectory would be. So that cannot be explained with the help of classical mechanics. But whereas if we are having the cricket ball and if we are trying to throw it with a particular speed, or we can say the momentum, then we know how and where its position and moment where its position will be. Then again but again At the same time, if we are talking about electron, then it would be very much difficult to have its position and momentum at the same time, and that is why we can come across the phenomenon we call it as a uncertainty, or the principle given by the Heisenberg. We call it the Heisenberg's uncertainty principle, and that principle we know true for a number of things basically energy and time, position and momentum for x coordinate, for y coordinate, as well as for the z coordinate. So these are the basics behind the quantum mechanics, and then we know how this Heisenberg's uncertainty principle leads. So like simply if we read this statement, then we can understand and we can explain with the help of the mathematical equations also. So like one cannot unambiguously specify the values of particles position and its momentum for a microscopic particle at the same time with exactness. So simply you can see delta x into delta px is greater than or equal to h by 2 pi, or we can say we call it as a h cross. So and simply we can define h cross and h by 2 pi. So you can see here position and momentum are therefore considered as compatible variables. So which means that either you can tell about position or we can tell about the momentum, but not both at the same time. Then again, Heisenberg's uncertainty principle strikes at the very heart of the classical physics, and that is what we know about the particle trajectory. Then another concept is here, like we call it the correspondence principle. So when quantum physics is applied to macroscopic system, it must reduce to classical physics. Therefore, the non-classical phenomenon such as uncertainty and duality must become undetectable. And again, so that is why the Neil Bohr's codified this requirement into his correspondence principle. So again, we know the duality just really explained by the explained with the help of simply de Broglie's hypothesis. Also, with the help of that, we can prove that lambda is equal to h by p, which means that light, if we are considering with respect to light, then we can say that light is having the wave nature as well as light is having the particle nature. But again, as we know, if we are having the wave nature more prominent, then we cannot tell about the particle nature, or it's not like prominent at the same time. So that is what the difference. And as we know, because of that, simply we can say lambda is equal to h by p, or h upon mv. So whereas we can say that both are having the inverse proportion with each other. So in that way, the Davison and Germer experiments proves the like a scattering phenomenon, as we proves the phenomena like as we know de Broglie's hypothesis have been proved with the help of the Davison and Germer experiment. So friends, again, as we know, wave particle duality can be explained. Means if we are considering the wave, then we know we are having the different phenomenon like a diffraction or the interference. But if we want to explain the particle nature, then really it is difficult to explain by using the similar theory, and for that we may require some different kind of the set of theories, and that theories are we can get in quantum mechanics, and with the help of that we can confirm the wave particle duality of the light. So these are some of the things which we can discuss about this. And now if we consider wave as a particle, so with the help of these all phenomena, what we can say, that what we can conclude, that if we are considering wave as a particle, then we can consider particle as a wave. And then again, because of that, there is a concept of matter waves comes into the picture. So again, we know, everybody knows, and even though in last lecture also I have shared how quantum mechanics emerges from the phenomenon of the black body. And again, there were a problem with respect to the spectrum of the black body, so they found some anomaly, and because of that there was the emergence of the new kind of mechanics. So that phenomenon we may be knowing about the black body radiations. And again, a number of laws associated with the black body radiations also. So simply the Wien's displacement laws, with the help of that, like we are having the formula lambda max into T is equal to 2.898 into 10 to the power minus 3. So this is what the Wien's displacement law, with the help of that we can calculate temperature, we can calculate the wavelength. And again, as we know, you can see, if we see the graph, so it was expected if we increase the wavelength, then there must be increase in a temperature or the relative intensity. But after a particular wavelength, so it is not happened continuously, and that is what the anomaly we can say that. Another laws we know in association with the black body radiation, and then that with the help of Stephen Boltzmann law, so some of the terms from the radiation can be explained also. So again, I'm not discussing in detail about the black body radiation spectrum, because our topic is like a quantum mechanics. Now you can see the crux of the quantum mechanics is, so there were two catastrophes, and one is like ultraviolet catastrophes, and that is what the biggest failure of the classical theories or the classical mechanics, and that gives birth to the quantum mechanics. So here simply if we discuss about these two catastrophes, then we can understand this is really important while solving the numerical. If we don't know these all, then really it would be difficult to find out the answer for MCQ type of the questions. So if we see about classical physics, then you can see emission spectrum, a superposition of electromagnetic waves of different frequencies, whereas frequencies allowed like standing waves inside the cavity. Again, as we know, if we are considering some cavity, then we can have some pattern of the waves. So that is what the expectations of the classical physics. But again, another theory we are just aware about, that is equipartition of the energy, that again gives some sort of the explanation in association with the classical physics. But finally, scientists found the anomaly in a spectrum, and that is what they called as ultraviolet catastrophe. And then again, that was solved with the help of quantum mechanics. And again, as we know, if we are talking about quantum mechanics, then Max Planck is the person who can be considered as most important scientist in the field of quantum mechanics. Why? Because most of the mechanics are dealing with the energy, and if we see the famous equation in quantum mechanics, that E is directly proportional to nu, and then we can equate this equation like E is equal to h nu. And then now you can consider, if there is no h, then how do we think about the nu? Then how do we relate this, like how energy is directly proportional to the frequencies of radiations, frequencies of the electromagnetic radiations. And that is why we can say that Max Planck has contributed a lot into the domain of quantum mechanics, and because of that he was honored with the Nobel Prize in 1918. And now if we see what he has explained, then simply we can see that means he has given some explanations, and then we call it as a Planck's radiation law. Again, these all things are related with the radiations, that is why I'm not touching much. But simply we must know the Planck's constant 6.62 into 62 into 10 to the power minus 30 point joule, 34 joule second. Then another concept is like a quantization, that also matters a lot in quantum mechanics. Now I'm coming to the most important phenomenon in quantum mechanics for which the Einstein secured the Nobel Prize. And that phenomenon is the photoelectric effect. And really, it's a very simple phenomena, but really it is important to explain and important to understand also. So simply here you can see, if some of the like here you can see light will fall on any of the metal surface, then there is a ejection of an electron, and now you can see that electron can be captured with the help of this particular plate. And again, because of that, we can see that there is flow in a current in a circuit, flow of current in a circuit. And that is what the phenomena, just like explained by the Einstein, and again for which Einstein secured the Nobel Prize. And if we see a photoelectric effect in detail, then you can just come across with the influence of light intensity on the photoelectric effect. Here you can see like a low intensity for which is with respect to frequency how it is, the number of electrons ejected you can see, and the energy threshold as we know. So how energy threshold is there. Then again here you can see in case of photoelectric effect, so when like light will incident on any of the metal surfaces, then there is a ejection of an electron, and that also can be explained with the help of the quantum mechanics. It is not possible to explain this particular phenomenon with the help of the classical mechanics. Now let us come to this basics of quantum mechanics we call as a photoelectric effect, and that we have seen like photoelectric effect. Let me recall what we learn about it. Like the photoelectric effect provides evidences for the particle nature of light. जैसे अपने को सबको पता है कि if we want to discuss about the wave nature of light, then we know we are having number of theories. We are having several theories that supports to the wave nature of light, like interference, diffraction, polarization, refraction, scattering. So these all phenomenon gives the stronger evidences as light can be considered as a waves. But now in case of quantum mechanics, we know we are having the dual nature. So now here we our intention is to prove that light can possesses the nature of particle nature also. And to prove the particle nature of light, so here we can see it also provides evidences for quantization. Then if light shines on the surface of metal, there is a point at which electrons are ejected from the metal. The electrons will only be ejected once the threshold frequency is reached. Means not at every case. So the frequency that must be in, or the light of the frequency that we consider as a threshold frequency must be incident on a metal surface, then and then only electron can be ejected. So again, below the threshold frequency no electrons are ejected. Then above the threshold frequency the number of electrons ejected depend on the intensity of the light. Now, here we can consider particles as a waves. And if we want to consider particles as a wave, then again simply you can see one of the experiment that we should just remember for solving the MCQ type of the questions, like Aharonov-Bohm effect. So that simply we can see here the peaks. Now, let us move ahead to the postulates of the quantum mechanics. So, simply quantum mechanics is nothing more but linear algebra and the Hilbert spaces. Now, simply as we know, initially I have shared, when we talk about the quantum mechanics, then quantum mechanics can be explained with the help of the wave mechanics as well as the matrix mechanics. And if we consider both the mechanics, then we need a algebra to solve the equations, and that can be solved with the help of the linear algebra. Or another thing is like a Hilbert spaces, in which we can consider the three dimensions, and with the help of different kinds of the notations we can solve the problem arises in quantum mechanics. Like again, what makes quantum mechanics like simply quantum mechanics is the physical interpretation of the results that are obtained. So as we know, we may obtain the results, but again it is essential to interpret the result which we have obtained, and that can be you can see. So that is what really essential, and that can be only possible with the help of the quantum mechanics. So now let us focus on some of the postulates of the quantum mechanics. The first postulate of the quantum mechanics is quantum physicists are interested in all kinds of physical systems. As we know, the photons. Photons is most important in terms of the quantum mechanics, and we can say that light can be considered as a quanta of photons, means bunch of photons. Then conduction electrons in metals and semiconductor, as we know how electrons are conducted. Once we apply the potential difference to the metals as well as the semiconductor, and even though how atoms can be behave. So these all kinds of the phenomenon can be explained with the help of the quantum mechanics. And then again, state of these rather diverse systems are represented by the same type of functions, and then we call it as a state functions. So now let us focus on the first postulate of the quantum mechanics. So the first postulate says that every physically realizable state of the system is described in quantum mechanics by a state function psi. So psi is again the function of x and t. X is the position, t is the time, or we can say that x, y, z, and t. And this psi can be considered as a wave function. So simply we can understand every physically realizable state of the system is described in quantum mechanics by a state function, or we call it the wave function, that contains all accessible physical information about the system in that state. So physically realizable states means states that can be studied in laboratory. So that is what we call as the physically realizable states. Then accessible information means what? The information we can extract from the wave function. And the state function means what? The function of position, momentum, energy that is specially localized for a particular region. So in that way we can explain the psi. And here you can see psi is nothing but the psi is equal to c1 psi1 plus c2 psi2. So if we are considering psi1 and psi2 represents the two physically realizable states of the system, then the linear combination will be equal to psi is equal to C1 psi1 plus C2 psi2, where C1 and C2 are arbitrary complex constants, represents a third physically realizable state of the system that we can add the systems likewise. So and simply because of that we called as a wave function psi of xt. So position and time probability amplitude. So even though we can write this psi of x, y, z and t, so that is also possible. So and finally we can say that quantum mechanics describes the outcome of an ensemble. I hope you know the term ensemble of measurements, where an ensemble of measurements consists of a very large number of identical experiments performed on identical non-interacting systems, all of which have been identically prepared so as to be in the same state. Second postulate of the quantum mechanics, so you must remember the postulates. So to solve the numericals in in NATE, SAT or GATE examinations. Second postulate is if a system is in a quantum state represented by a wave function psi, then this P dV is equal to mod of psi square into dV. So is the probability that in a position measurement at time t, the particle will be detected in the infinitesimal volume dV. So simply again we can note that mod of psi of x t square is nothing but the position and time probability density. Here we are using the term position and time probability density. And here we can say that the importance of normalization follows from the Born interpretation of the state function as a position probability amplitude, and according to the second postulates of the quantum mechanics, the integrated probability density can be interpreted as a probability that in a position measurement at time t, so we will find the particle anywhere in space. So this is the again importance of the second postulate of the quantum mechanics. And again, as we know, if we go in deeper sense, then there is a phenomenon we called as a one-dimensional potential well, where we can find out the means the position and momentum of a particle by using certain quantum mechanical phenomena. Again, if we want to elaborate the second postulates of the quantum mechanics, then we know the normalization condition for the wave function is Integration of P dV is equal to integration of mod of psi of x y z or square into dV over the volume V, and that can be written in terms of psi and its complex conjugate like psi asterisk xyz into psi of xyz over the volume dV is equal to 1. So now let us understand what are the limitations on the wave function. So simply now we can understand wave function is nothing but the psi of xyz into t, z t. But really, we cannot imply or apply the wave function everywhere. There are certain limitations for the wave function, and now you can see the first limitation is only normalizable functions can represent a quantum state, and these are called physically admissible functions. So you must remember this. Only normalizable functions can represent a quantum state, and these are called physically admissible functions. State function must be continuous and single valued function. So again, this is the limitation. State function must be continuous and single valued function. Then again, state function must be a smoothly varying function, like we can say that the continuous derivative. So this is the second postulate of the quantum mechanics. Now we can discuss about the third postulates. So every observable in quantum mechanics is represented by an operator which is used to obtain physical information about the observable from the state function. For an observable that is represented in classical physics by a function q of xp, the corresponding operator is q of x dash p dash. So for which you can see like a position is the operator is x into cap x cap, then the momentum is p cap is equal to h cross upon I del x, then energy is E is equal to P cap square upon 2m plus V of x cap is equal to h cross square upon 2m into del square upon del x square plus Vx. So simply if we want to see the illustration of these all, so an operator is an illustration, a symbol which tells us to perform one or more mathematical acts of a function, say f of x. The essential point is that they act on a function. Like operators act on everything to the right unless the action is constrained by brackets. So addition and subtraction rule for the operators. Again, operator is most important. That is why we are discussing it. Operators commute if they obey the simple operator expressions. Okay, again, if we want to discuss more on operators, then we know there are different operators in quantum mechanics that can be used as per the requirement for solving the mathematics. It helps us a lot. So the requirement for two operators to be commuting operators is a very important one in quantum mechanics, and it means that we can simultaneously measure the observable themselves represented with these two operators. The non-community commutativity of the position and momentum operators, the inability to simultaneously determine particle's position and its momentum is represented with the Heisenberg's uncertainty principle, which in mathematical form is expressed as delta x into delta px is greater than or equal to h cross by 2. So is equal to 1 by 2 into h cross means h cap dash p cap, and that can be generalized for any pair of observables. So again, the fourth postulates of the quantum mechanics. So simply as we know, in 1926, Erwin Schrödinger proposed propose an equation that describes the evolution of quantum mechanical system. So SWE, which represents quantum equations of motion and its form. So like simply we know minus h cross square upon 2m. That comes from the one dimensional potential well also. Del square psi upon del x square plus vx into x vx of psi into xt. So that will be equal to minus h cross square upon 2m into del square upon del x square plus vx. So psi of xt is equal to I into h cross del psi by del t. This work of Schrödinger was simultaneously simulated by a 1925 paper by Einstein on the quantum theory of ideal gas and the de Broglie theory of matter waves. So simply we have to remember this note. Examining the time-dependent SWE, one can also define the following operator for the total energy. So simply therefore total energy is equal to E is equal to I h cross del upon del T. Then again, fourth fundamental postulate of quantum mechanics, the time development of the state functions of an isolated quantum system is governed by the time dependent SWE. So h cap cross into psi is equal to I h cross into delta I h cross upon delta t, where h cross is equal to t cross plus v cross is the allium is the Hamiltonian of the system. So note on isolated system. The TDSWE describes the evolution of the state provided that no observable and no no observations are made an observation after the state of the observed system, and it is the DSWE cannot describe its changes. So here just I want to stop for today. As sir also sir needs to rush to his home, so we can finish here. So now just for next 10 minutes is for question and answer. So your question and answer and the suggestion. I am watching you all on YouTube. So please give your suggestions. That will be much important for us.